Okay. What we're going to move into now, so this is end-of-life decision-making at the sort of consumer level and sort of at the design level, right? Because you can use those product declarations as a guide for environmental improvement in design. Got option A, option B, make some comparisons, make a judgment, move forward. You can use it from the consumer end. Here, what we're actually talking about is much more of an end-of-life perspective. So I have a coffee maker coming in. I'm a disassembler, or I run a garbage collection company, and I'm thinking about starting a recycling business or something. And I'm thinking about a coffee maker that is at its end of life, and I'm trying to decide what's the best thing to do with it. Okay, so it's not exactly the design perspective, and it's not the consumer perspective, the use phase perspective. It's the end of life perspective. Okay, and that's what we're taking here. And I've set this up already. We're thinking about how to, well, first of all, methods to do optimal decision-making at end of life. And we're thinking about how to handle multiple situations. So in this case study, we're thinking about a coffee maker that might be used and disposed in Aachen, Germany. This is near the Dutch border in the west. And Ann Arbor. We're actually comparing the Aachen and Ann Arbor situations, scenarios for end of life. Okay? So what I'm going to cover here is the state of the art as it was about 5 years ago. It hasn't progressed that far since then. And then to go through a sort of a 6-step methodology to establish optimal end-of-life decisions for this coffee maker. And then we'll look at some results. So we'll look at the Ann Arbor case, we'll look at the Aachen case, and then we'll do a sensitivity analysis. Transportation costs, labor costs, transportation distances, all important when you compare the US case to the German case. We'll also look at the impact of the WEEE directive, the Waste Electronic and Electric Equipment Directive, and then try to say some things at the end. Okay? So I've covered the objectives already when I was getting going today. I mentioned that if you wanted to enumerate all the strategies and then just pick the best one, it would take you 20 years, computer time. So even with a product that seems really simple, the minute you just open up any decision, any disassembly sequence, and then for any component, it can have any fate. It's a combinatorial problem that just blows up. So we need methodology, and I'll just say up front that we're using a genetic algorithm here. All right, and I'll say a little bit more about that in a few minutes. Once we have that methodology to rapidly calculate the best options, so how many people know what a Pareto set is? Okay, more than half. So can somebody give us a definition of a Pareto set or a Pareto front? Go ahead.
It's where you can't make one thing better without making something else worse.
Exactly. So I'm not interested in 3 million disassembly decisions. I just want to know those decisions that aren't, for which there's no better decision on one axis or another. So let's suppose that we're looking at energy recovery and cost at end of life. So if I have 100 kilojoules I'm getting back from the product, and that cost me 50 cents, and that point is on the Pareto set, it means you can't recover that much energy cheaper. It's just the best trade-off you can make between energy and cost. And what this methodology does is it establishes that front. And in doing so, sort of cleverly using genetic algorithms, you can get that front established fairly quickly, which allows you to do extensive sensitivity analysis. I'll show you what the results look like a little bit later. Given that, then, let's look at the sensitivity of these Pareto sets to situational variables. So let's suppose transportation costs were low or high, labor costs are low or high. What would that mean for my optimal disassembly strategy? Okay. So this facilitates decision-making under uncertainty. And we wanted to see if we can come up with a graphical form, sort of a visual scorecard. And we came up with one, but don't get your hopes up. It's kind of messy. All right. Everybody understand what we're trying to do here? It's clear? Okay, so let's just talk about the constituent disciplines that are required to do this kind of analysis. The first area that this touches on is disassembly sequence planning. So this is not a new field, disassembly sequence planning. It means what order are you going to disassemble? Often, how much are you going to disassemble? So maybe I've got a valuable piece of aluminum, or I've got some component with precious metals in it, and I want to get to that component. How can I get there most efficiently? It's a fair amount of math and operations research that ask questions like that have made some progress. Okay? But what hasn't been done is really look at the environmental dimension beyond just trying to get some component out that might be environmentally sensitive. So what this work that I'm going to present here does is it actually looks at trade-offs between economics and the environment. So this is, our environmental sustainability case we've been talking about all term. So we're incorporating economic and environmental objectives together. It's a multi-objective optimization problem, for those of you who know what that means. There have also been a lot of coffee maker case studies, but none of which really focused on the end of life. So this contributes to that literature also. And in the disassembly sequence planning literature, there's very little planning under uncertainty or optimization under uncertainty. So this is contributing there too. Okay, and very little sort of use of Pareto sets. So we have a whole bunch of ideas, and in this work we're pulling it all together and hopefully making some progress. All right. Looks like my battery's died here. Oh no. All right, good. So it's a 6-step process. Okay. So the first step is that we're going to define the situational variables. So one variable might be transportation cost, another might be labor cost, another might be transportation distance. When we take the set of situational variables together, we call it a scenario. Scenarios are handy because I can just throw around a label like the Ann Arbor scenario, and you kind of have a sense what I'm talking about, even if I don't list all the situational variables. I can talk about the Aachen scenario, and you kind of have a sense of what I mean. Or you could talk about the Ann Arbor scenario with no transportation costs, so free transportation. That's a scenario. So you can communicate these things a lot easier if you can group your situational variables into a scenario. So that's what we're doing here, defining the scenarios of interest. First step. The second step is then to define the product structure, because remember, we're going to disassemble this thing. So you have to be realistic. If your part of interest, whether it's environmental interest or cost interest, if it's in the, or I should say profit interest, if it's in the middle of the assembly, you usually can't just reach your hand in and get it. You got to do some disassembly previous. So what it means is you have to establish a feasible set of orders that you can arrive to that component. Okay? And there's almost always more than one way to get there. So you can see that this really blows up quickly in terms of its dimensionality. So you need the product structure represented mathematically. You need the feasible set of disassembly sequences represented mathematically. And you also need to establish the disassembly times. So we did this for a real coffee maker, and a graduate student working with me spent about 2 months disassembling this coffee maker and timing and bringing his friends in to do operations because he was getting really good at it and he didn't trust his own time studies. Just to see, okay, for each step, what is the disassembly time for that step? Now, in this coffee maker case study, we were lucky because basically once you got to a disassembly step, it didn't really matter how you got there. The time to take the next step was the same. So the disassembly time for any given component was roughly the same. So we were able to make an assumption that really makes the math a lot easier. I mean, you can imagine, just think of like a laptop computer and just say you can go into it and come from the bottom or come from the top. It's not a given that the product you're taking out from the top you could take out in the same amount of time from the bottom if that was the step you're on, right? So there might be clearance issues and other issues there. But for a coffee maker, it turns out to be a pretty good assumption. It also simplifies the math. From here then, you've got your disassembly structure. Now you need an evaluation model. So, okay, I'm going to disassemble the coffee maker. What's the cost and what's the environmental benefit? So you develop those models of environmental cost and economic cost. Step 4 then is to pose this as a multi-objective optimization problem and develop metrics for disassembly time, which I've already talked about, your end-of-life economics, and your end-of-life environmental impact. All right, so you pose that, and I'll show you what the math looks like. Then you just go run the genetic algorithm, get your trade-off set, and try to interpret the results and make it graphical. Okay, so that's a 6-step process. Now what I'm going to do is go through each of these steps at sort of a high level so you can get a better idea of what we're talking about here. But are there any questions before I do that? Is this clear? Yeah? Okay. So I think I've defined all these terms, but just in case they're not clear, let me do it again. Disassembly sequence, it's not just the order. I should say it is the order. I should take that back. So it's the order in which you're disassembling the coffee maker. Now you may not have any disassembly. You might just throw it to a landfill, or you might just shred it. Okay, those are strategies. An end-of-life strategy might just be landfill it. It might be shred it. It might be disassemble in this order, and then with those components that were disassembled, landfill them for the rest, recover and recycle them. Okay, so we call the end-of-life strategy is the whole sequence of decisions that are made at the end of life. Situational variables I've defined already. Right, it's like your transportation costs. The scenario is your collection of all situational variables. Okay. So this is a lot easier than the 6-step process, just a graph, right? So you need your scenarios, you need your product model, you need your evaluation model, which gives you environment and cost. Then you make your optimization problem, solve it, and then try to interpret it. I mean, it's just pretty easy, just the devil's in the detail. So how does something like this get done? First, well, let's define situational variables, end-of-life strategies of interest or scenarios of interest. It's a coffee maker. We're interested in comparing the scenario in Germany to the scenario in the US. We think that these market variables are important. Recycling prices, transportation prices, labor prices. The infrastructure is really important. I might have to, if there's say an aluminum heating tube inside the coffee maker, and I want to recycle that. Well, I might have to drive 900 kilometers in the US to get that aluminum recycled, and I may only have to go 75 in Germany. It's going to make a big difference. So infrastructure is really important, as well as your transportation method. How big is the truck? Is it going by rail or ship or anything? And then your recycling technology and efficiency, right? If you've got disassembly tools and expertise, you might be able to do this faster. In this case study, we're not looking at that particular topic. We do look at take-back legislation, and we didn't look at taxation or subsidies, but you could also, in this framework, easily incorporate those. Did we miss anything? These look like relevant factors for the environmental and economic evaluation of end-of-life coffee maker. Everybody understand? Okay, and only a few of you have seen this before, but this idea of defining a product structure in a way that a computer can understand it. So basically the first thing you do is you figure out the components, what are they, and what are their material compositions, because here we're talking about recycling for energy. We're not looking at remanufacturing. We very easily could have, but we had a hard time thinking anybody was going to remanufacture a coffee maker, so we just didn't bother with it. Here we're looking at recycling for energy recovery. So once you know the components, then you basically develop a liaison graph. So this is the connectivity of the assembly. And from the liaison graph, you can basically define a precedence matrix. What a precedence matrix is it means you can't remove B before you remove A. So it's actually a matrix of ones and zeros that defines whether one product needs to be removed before you get another one out. From that, you can process feasible set of disassembly sequences. And I'll show you what precedence matrix looks like in just a second. From there, then, if you know, if you had a sequence in mind, then you're able to calculate the total time and total cost. Okay. So this is a liaison graph. So basically, you're looking at sub-assemblies. We're numbering them 1 through 12. Okay, and there's about 35 parts when you take it all apart. Okay, so we give them numbers and we give them sub-assemblies here. What we're assuming is once you get the sub-assembly out, then there's only one optimal strategy for the sub-assembly. What that does, and that's a reasonable assumption, if I take the glass pot out, there's basically one optimal strategy for that glass pot. All right. That simplifies things a little bit. If we do it that way, at least in terms of communication, there's 35 total parts. As you can see, this is a fair amount of work, even for a simple product. From here, you can figure out, all right, if I'm going to get the filter out, right? I need to go from the lower housing here. I need to separate out the upper housing, and then I'm talking here about the filter casing, not the filter itself. You can just open the lid and take that out. But what houses the filter, right? You got to go in, and there's at least 3 steps to get there. Go ahead, John Michael.
Is that just by?
It's somewhat arbitrary, actually, but you try to minimize the connections to other things. So once it's separated, it's separated. So it's arbitrary. You could do this in a number of different ways. This was purely, okay, here's the glass pot. That looks like a sub-assembly. Great. The upper housing, basically 2 halves. You can pull them apart, get 2 sub-assemblies. But within that sub-assembly, there's another one. So now, we're going to define another sub-assembly off the upper housing. So it gets pretty technical when you get into it. I just want to give you a visual of the kind of work you need to do. Go ahead, Amanda. Oh, these are part numbers that we gave them. So just the individual parts. So your PVC rings, number 10. This is just a bookkeeping indexing. So it doesn't have a meaning really besides that. Go ahead, Kelly.
Is there a starting point?
We don't tell the optimization routine where to start. But just about everything requires you to remove the glass pot. So that's usually where it starts. But if you just wanted the filter out, you wouldn't need to remove the glass pot. So that's all up to the magic genetic algorithm. We'll call it magic here, so we're not going to talk about how we do it. So this is a precedence matrix. The columns here are what the target is, or I'm sorry, what you need to remove to get the subassembly, if you will, in the rows. Okay. So for instance here, if I want to remove basically anything except number 3, which number 3 is your copper filter. Sorry. All I need to do, I basically don't have to do anything. I've got a lot of access up front. But if I want to get number 3 out, I can't just remove the number 1 is the lower housing here. Okay. So it's what you're removing to get which part. And you can basically go from here, and this is where the whole field of disassembly sequence planning is manipulating matrices like this and doing optimization with them. Right? And even in our paper, which is one of the optional readings, I think it was 25, we don't even talk about how to do it. Right? But once you have that product structure, then you need to evaluate. Okay, what's the economic impact of a strategy amidst a given situational variable? So it's not just the strategy. The strategy depends on the situational variable. So what we're trying to show here is how we get the environmental metric and the economic metric out from an end-of-life strategy coming in with a corresponding set of situational variables. The model will cover the disassembly, the shredding, the recycling, the landfill, all the components. Okay, so recovered material over to the right, waste materials over here on the left. Okay, so this is step 3. The situations we looked at here at the bottom, we're looking at plastics, glass, steel. We're looking at the distances to recover those materials. And then on top, we're looking at the prices per kilogram that you can fetch from the recycling process. Okay? We are not showing on this graph the amount of energy that's recovering from the recycling process. That came from life cycle assessment databases specific to Germany and specific to the US. You see here the distances in Germany a lot lower. The labor cost a little higher. The transportation cost a little higher per ton kilogram, or I'm sorry, per ton kilometer. Tipping fees much higher in Aachen, 10 times higher. Okay? So these are the situational variables here that we're looking at in the case study. Making sense? Then you formulate an optimization problem. Here it's, again, multi-objective. So you're trying to minimize environmental impact. What that means is maximize energy recovery, because that's the only thing we're looking at here. This is a general formulation on the slide. Now, X is your decision, end-of-life decision. What's the disassembly sequence? What happens to the end-of-life fates of each component? So X is a set of decisions. And that's what you're trying to optimize. S is the situational variables, like we just looked at here. Okay? And our constraints, for those of you who know a little bit about optimization, you have to have a feasible end-of-life strategy. So your disassembly sequence has to be viable. Your, you can't recycle something that's not recyclable, for instance. So, basically, you've got to, there's a set of constraints here that need to be represented. The precedences here, this is the disassembly sequences. Regulations, do you have a WE directive or not? Okay? And again, we used a genetic algorithm to solve this. All right, so this is what we've been waiting for, the answers. And, it's like, okay, this is a mess, right? It kind of is, but if you stick with us for about 4 or 5 minutes, it begins to make a lot of sense. And a graph like this says a lot. Okay, so let me explain to you what we're looking at. So this is the Ann Arbor base case for the coffee maker. Now, what you're looking at is P is the maximum profit, assuming you do any disassembly at all. Okay, and then E is your maximum energy recovery, and that is always you take the whole thing apart and recycle the whole thing. In between is a Pareto front of strategies for which you cannot basically move in the outward direction this way, meaning you can't, for the Ann Arbor case study, achieve 140 megajoules recovery at a profit. This is negative. This is cost. So 0 is up here. So this is all cost down here. And your costs, they're not crazy bad. They're like 30 cents to about $1.50. So $1.50 to take the whole thing apart and recycle the whole thing. Okay, and you get, for that, that's your strategy E here, about 130, say, megajoules back for doing that. Okay. Now, the triangle up here is just landfill. It's pretty cheap. And you certainly don't get any energy. In fact, it costs you energy. That's why this is just a little bit to the right of 0 up here. S is shredding. So with shredding, just send it to the shredder. You actually get energy back, a considerable amount, and even a little bit of money. Very little bit, maybe 10 cents, 5 cents, somewhere in there. Okay? And then what we're showing down here below is, okay, if I'm going to do some disassembly, strategy P, basically I just perform steps 1 and 9. I think that's the upper housing and the glass jug. Remove the glass jug. Okay, so that maximizes your profit. There's a midpoint strategy M that we define, and that is just taking the price of electricity and showing how much electricity costs. So this M is a reference. And if you're below this, it means you're spending more than your grid to get a certain amount of electricity. If you're above it, it means you're spending less. So it's a reference line. Andrew? Well, you're shredding. What is a shredder? Is the main question, right? So you basically got a machine. It may be hammer mills and various ways to make the product into small bits. Then you might have a set of magnets around to take the ferrous stuff out. You might have an eddy current separator there to get the non-ferrous material separated. Then you might have a flotation system that gets the plastics out, depending on how elaborate it is. So it's basically mechanized, automated. You could call it automated disassembly in some way, but it's a very dumb way to do it. You just break up the whole product and then let it's not robotic, I'm looking for a word, sort of mechanical separation, right, to occur. So that's what's happening in the shredder case. And you could do this for cars, auto hulks get shredded and refrigerators get shredded. Of course, all the CFCs go into the atmosphere if you do that. So that's an issue with refrigerators, and you can do it with the coffee maker. Other questions? Go ahead. Yes. So here we're assuming that you've got local disassembly and recycling options. Okay. Actually, let me take that back. It's just local disassembly. So imagine you had a disassembly factory in Ann Arbor. Instead of having to travel back to where it was produced, which is in this case North Carolina, you have a network of disassembly factories that are local that handle the waste. So we think that this local scenario would be a little bit more realistic than taking a whole coffee maker and shipping it back to Wilmington, North Carolina, whatever, for disassembly. Right? But that doesn't really exist in the US, but you do have that model in Europe. So, and if you have a local disassembly factory, let's call it that, then you can actually make a little bit of money. But you don't get really much more money than shredding, even though you get more energy back. Now your cost component here is, if you do any labor or any disassembly at all, the max profit, what we're just showing here is that it's mostly labor you're paying for. Okay? Does everybody understand how to read this graph, what it's saying? Go ahead. That's this strategy.
Yeah, so on the negative x-axis,
It costs money.
So the amount of money you would pay.
You would pay to have it to recover this energy through recycling.
And what are the mechanisms by which you would get energy back from this?
Well, it means you avoided producing something else.
So it's mostly that.
Yeah, no, it's all of it. We did not look at incineration of plastic. We could have. Other questions? Okay, so now once you're able to do this, and we assume local disassembly, we could do this until the cows come home, right? But it's fun because you can look at, in this case, transportation costs. Like, how important are the costs of transportation? Well, if you're assuming a local disassembly, it doesn't make a whole lot of difference, right? I think that's what you gain from this. But it might determine which side of zero you're on, which might make a big difference if you're trying to tell somebody else what to do. Now, what you're looking at over here on the right is fairly informative because it looks at how robust your strategy is to cost. So here you're looking at the cost of transportation, basically from free transportation up to 2.5 times the base case transportation cost. And what you see here is your strategy in terms of what you do doesn't change. Your profits go down as transportation costs go up, but your strategy doesn't. Until you get to a magic number here just above 2 times, then your strategy changes. You go from the base case strategy to the 250 strategy. So, and that here, what it says, that your base strategy is just recover the upper housing and shred the remainder. If the labor costs get too high, then you just recover the copper filter and landfill the remainder. Right? So you can begin to get a sense of, how, if this were done during the design stage, and this information followed the product. Now, somebody at the end of life, 5 years later, they wouldn't have to go back and study exactly what the coffee maker is to figure out what to do. That information would be almost instantaneous, assuming the person on the other end knew how to read this. Right? That's what we were after in this study, was to be able to do things like this. How sensitive. So you have in your manual, okay, this is the base case. And now, well, 5 years later, the transportation costs are a lot higher, so I'm going to use this strategy here. Right. This is making sense, what we're trying to do? Now we're looking at labor costs. So transportation costs affect the, let me say, it's like a translation. I mean, not exactly, but it kind of moves things up and down. Labor costs change the slope. So, and that kind of makes sense, because if you're doing more disassembly under a high labor cost, then your costs are going to fall very quickly. So this changes the slope. And we have the same sort of thing over here. You see that your profits, as the labor rate goes from 0 to 2 times, 200%, your costs or your profit are going to go down, and your strategies are going to change, right? So you're looking at the circles are energy, and the profits are square. Right? Now the interesting thing here is if you had free labor, I mean, I don't think it's ethical to use prison labor, but I mean, if you have free labor, right? Just imagine it. You actually would have your incentives lining up. So your maximum energy recovery strategy would be the same as your maximum profit strategy if labor were free, which it never is. Okay? So you can gain some insight into these things. Like labor gets more expensive, you know where that equation's heading. Okay? Now, here we're looking at the consideration of we. Okay, let's say you got to recover at least 70% of the coffee maker by mass. Now, what do you notice if you compare the Ann Arbor? If you just compare the we case with the local case, what jumps out at you? So this is just Ann Arbor local with and without we. So if you just look at this cluster up here, what jumps out? Say again? Yeah, you go from a profit to a loss. What else? Is this line longer or shorter? So under we, it's shorter. So you're constrained. Your options are constrained, which they naturally are, because you got to recover 70% of it. So clearly, I mean, this is sort of obvious. It's going to affect costs, and you can nail that right away. As well as this again was under the local situation, and then this would be you're shipping the coffee maker back to North Carolina. This is the Aachen case here. Okay, and if you put the two, if you try to represent all this information on one graph, you can see it kind of gets messy, but if you know how to read it, it's not so bad. So here's your base case. If you drop so aluminum turns out to be a big part of the story. So if you can recover aluminum, that's really good, cost-wise, and it's pretty easy to get the aluminum out. So the aluminum scrap value is going to be a big determinant. The labor rate is going to be a big determinant. If you have a recycling target, that's going to be a big determinant. So here we're just overlaying 6 scenarios, and then at the bottom, we lay out what the strategies are. Now it's coded, so you can't quite see it, but basically you're covering here all of the European and U.S. situations, distance-wise, cost-wise, recycling value-wise, and what have you. And you see that the story is not dramatically that different. Therefore, if you study it long enough, you can have a pretty clear picture of what to do with your coffee maker at the end of life. Okay. So this is a fairly straightforward type of analysis. Now, if you're not happy with the way this graph looks, what do you do as a designer? Redesign, right? I mean, if you see that, you know what, the labor cost is really important here, then you work to design, in the design, to minimize your disassembly times. Right? Straightforward. So you can certainly use this as an input to design. And that was a major motivation for this one.